So we're in the middle of doing the mass transfer stuff, and I worked out this stuff for multi-component systems, and that's probably going to take more than one day, just based on our rate of progress, right? So we are here with this, and I thought about just skipping these exams, but this example on force convection is kind of important to put into perspective. We're going to talk about free convection. I decided I want to finish this example from last time, and then we'll start in on this today. And I assume we're going to get to here, somewhere, and then we'll finish this on Friday. Okay, and then Monday we'll have our review, and then Wednesday. Okay? I promise we really will have an exam. I'm sure you're all not that upset. And then there's no other homework problems for this, because I don't care to go make up more homework problems and homework keys. Okay, so the homework is to start studying for your exam. Okay, so think up some questions to ask me, and we've kind of I think had kind of an easy homework load because we've been going so slow and I haven't had homework problems. So I'm hoping that you spent some time reviewing your notes and reading the book and doing some of this other stuff. So if you haven't, now would be a good time to sort of go back and review that, because I sort of assume that, I don't know what they say about assumptions, but that the stuff I do in class is certainly fair game for an exam, right? And so if we repeated a derivation or did a slightly different derivation, that's not something I'm going to do in a homework, but I expect you should be able to do something like that. Okay? So unlike undergrad, maybe where you do a little derivation to motivate this equation you're going to plug in. Right? Here we actually are learning about where these equations come from and that sort of thing. So that's fair game. Okay. So if you're feeling like you're missing transport on Saturday, well, I can always send you more problems to you. If you want me to, give you the key for an extra problem you did because you were just so bored, that would be fine. Anyway, so I just wanted to give you a heads up. I hope this isn't too obnoxious that it's a little bit disorganized. It feels a little disorganized to me at least. Can I get a volunteer for a prayer or lecture day? Wait, Brian.
Dear Father, we're grateful for the opportunity that we have today to be able to come to class and learn more about transport. And please help us that as we learn this material and start preparing for the exam, that we may know the things that we need to know. We ask for the things in the name of Jesus Christ.
Amen. That reminds me. So I will, maybe we have our exam review. I will make a sheet. I'm working on it now, but it's not done. That will have a list of the things from the lectures I expect you to deal with. I made one of these in fluids. If you remember, I had like 2 columns of things you should know and things you should know. Okay? So I'll make that same kind of list. It's useful for me as we go back and think about it. And I think it's also useful for you to go back and review. That's what he thought we were supposed to get out of that. Okay, well, I better ask about that thing, right? So, anyway. Okay, so last time we have gone through mass transport equations for a couple of lectures, and we were doing some examples. And last time we ended, we did a solid sphere that was dissolving, right? And we did the really easy case where there was no velocity. We had to dilute solution and it was sparingly soluble. And then we did the case where it was, easier to dissolve, and we saw that led to a convective flux from our diffusion, right? And then in your homework for today, if I'm not mistaken, you did a case where you did the sphere dissolving where you had a chemical reaction going on, right? And you had to solve that problem, okay? So now I want to turn and think a little bit more about convection and what happens if we've got coupled mass transfer and fluid mechanics. We're going to do an example of that. Then we're going to sort of step back and talk about, okay, what happens if I have multi-component systems and I've got heat transfer and I've got mass transfer and I've got fluid flow. What do all the equations look like? What's their general form? And what we're going to see is that we can write it down, but it's nasty. And you're never really going to want to start there, kind of like I said last time. it's so gross. I mean, you should know what all the terms are, but you're really only going to retreat to that if you have to, okay? And then we're going to see, though, that leads us to a different kind of approximation we haven't seen yet, the Boussinesq approximation, which allows us to look at variable density without having to solve the fully compressible nastiness from there, okay? And we'll do some quick dimensional analysis so we can know what the Grashof numbers are and these other numbers that are in there. And then we'll do a couple of examples on free convection, okay? So that's where we're going. So, and hopefully here we'll sort of have a better understanding of how convection and diffusion play together and what are the different cases that can go on when we're solving these problems. So let's look first at the forced convection example. So this is, 1E3, right? Forced convection. Maybe before I launch in, are there any questions about the overview I'm laying out here? No? Okay, great. Okay, so this is an example from the book. I thought it was a nice example. So let's assume we have a tube here, okay? And so there's fluid flow coming in, and we've got some catalyst here that's just on the surface. So, you painted a catalyst around the inside of that pipe, okay? So it's just kind of here on the surface, all the way around, right? And suppose we have some solvent S flowing, okay? So we got water or whatever it is we're pushing through, and then there's some component A in there, right? And A undergoes a reaction to B on the surface of that pipe, okay? And let's suppose that A goes to B is fast and irreversible, okay? So such that we'll be able to have a boundary condition where CA equals 0 at R equals R. That's what we mean when we say fast and irreversible. We don't want to have to take into account the reaction kinetics, okay, at the interface. We could go back and do this problem again, doing that, but that would complicate the problem. Let's do the easy one, right, to get some intuition about convection instead of worrying about the convection reaction. Okay, and then so coming out here now, there's going to be A plus B plus solvent, right? Okay, so what's going on here is that I don't know if we do a forced convection problem in heat transfer. I don't know if we did an example. You can go back and look at your notes. I had one in my notes, but I don't know if I got to all the examples I was going to do that day. So, but what we're going to do here is we're going to write down both the Navier-Stokes equation and a reaction diffusion equation, okay? And we're going to make some assumptions and we'll talk about that. So let's write those down. So the Navier-Stokes equation is rho B P is equal to minus grad P plus mu grad squared V. Am I missing anything? Yes, we often call this one. Well, we don't have any gravity here, flat. Okay, and then the reaction diffusion equation is D. Oh no, I'm doing this one in the mole units. So I have to write C dxa dt plus V star dot grad xa is equal to, and then is it C dAB grad squared xa. All right. I guess we've been writing this one del dot C dAB. I haven't assumed that it's dilute yet. And then there's reaction plus RA minus, and then there's XA sum over B RB. Okay, yeah. Okay, so that's our species reaction diffusion equation. That one's just for A. Okay. So that's our reaction. Okay, so what are we going to assume about this problem? Okay, so let's assume some sort of things that we would normally assume to get pipe flow out. Let's assume steady state. And we'll assume it's unidirectional flow. Okay. We'll assume unidirectional flow implies, at least in the flow profile, that it is, what's the one where it's independent of the z direction? Oh, I'm blanking. Fully developed. Thank you. That's the word I was looking for. Okay. What else do we have on here? Let's assume, no reaction in the bulk, so no homogeneous reaction. And let's assume dilute A, and let's assume that a constant number of moles. Okay, so we'll assume that this reaction A goes to B, right? That's just producing the same number of moles, so that's homogeneous. Okay, so if we do all that, what do we get out? We get out, let's write the one for the Navier-Stokes. We'll come over here. We get 0 equals minus dp dz. I guess we probably better put coordinate system up. I don't know if I have it. We'll call this z direction, that r direction. All right, so we better call that r equals big R right there. Let's call that one z equals 0. And that one z equals L. Okay, so we'll put that on our thing. Okay, so minus dp dz, and then we should, if we have unidirectional flow, right? This whole thing goes to 0, and we should only get out something that's vz of r, right? Because we shouldn't depend on theta on z, and so we should just get plus mu, and then 1 over r d dr r dv dr. If I remember that squared in cylindrical coordinates, right? Yep. Okay, so that's the Navier-Stokes equation. Okay, and then let's think about this one. So we said steady state, so that guy's 0. And we said dilute, so that piece comes out, and there's no homogeneous reactions. So we should get v star dot grad xa is equal to c. Oh, I forgot the c over here. Put the c out front. And then c VAB grad squared xa. Right? And I can cancel. I can pull the C in if I want. That'll make my life easier. So I'm just going to rewrite that here, but maybe you put that as a separate line in your notes. I'll put the CA right there, the CA right there, and drop the C right there. Okay? All right. So I have this problem, okay? And the problem is that this is a V, which is a mass basis, right? And this one is a V star, which is the mole basis. So I got to figure that out. So what I'm going to say here, remember V star is equal to XAVA plus XBVB plus XSVS. And V is equal to WAVA plus WBVB plus WSVS. Okay, and now I said it was going to be dilute A, and let's assume that the reaction doesn't happen so much, that can only have dilute B as well. So in that case, that means that XS is going to be about 1, right? Because it's mostly solvent flowing through there. So if XS is also 1, I can also assume WS is about 1. So that means that V star is approximately VS, which is approximately V. Okay, So I'm just going to let them be the same thing. All right, it'll make my life easy here. So this will then turn into a V instead of a V star. So I can rewrite that one then as V dot grad CA is equal to DAB grad squared CA. And then we need to worry about these guys. So get some more space. Okay. So remember that, so grad CA, that's going to equal dCA dr 1 over r dCA theta and dCA dz. And let's see. Okay. And then V, right, is dr theta z. So let's think about this. So we're going to do that V dot del CA. Okay. So we know that it's by symmetry dCA d theta is 0, right? So that term in the product is going to go away. And we also know that V r and V theta are equal to 0, right? Because we don't have any V, velocities going outward. We don't have any velocity spiraling around. So the only term that's going to survive in V dot del CA is going to be the Z term. VZ dCA dZ. Yes.
And fully developed doesn't cancel that in this case.
It's a VZ, right? Okay, but the fully developed, that I meant in terms of velocities. Okay. Because here I've got a concentration of A. Down here I'm going to have a different concentration of A. So, that can't be the case for that one, right? For their concentrations. Otherwise, the problem would be, I think, done. We would just have A convecting, Okay, so that's going to go on the left-hand side. On the right-hand side, we need grad squared CA, and grad squared is 1 over R d dr R dCA dr plus 1 over R squared dCA theta squared plus dCA z squared. All right. So, okay, so that one now, this one is going to be 0, right? For the same reason here that dCA d theta was 0. And now so we can rewrite our equation VZ dCA dZ is equal to this diffusion coefficient. And I guess it's not DAB really, it's DA in the solvent, right? So, the diffusion of A in the solvent is the relevant diffusion coefficient, not the diffusion of A and B. So I noticed that in my notes there. And then we have 1 over R d dr R dCA dr plus d squared CA dz squared. Okay. And then we have this problem CA equals CA naught at Z equals 0. So that's right here. I would have CA naught. And then I need CA to be bounded at R equals 0 and CA equals 0 at R equals R. Okay. And then this VZ I'm going to need. And VZ we can get by doing the Navier-Stokes equation all by itself. So what's nice about these forced convection problems is that this one now we can solve first, right? Before I have to do anything with this guy. So we've solved that at least twice in the class. So I'm just going to write it up. So VZ is VZ max times 1 minus R squared over R squared. Big R squared. Okay, so we can just take that and plug that in there. Okay, and so this is the force convection problem in the book. Okay, so this is where I'm going to stop this example. We get to here, I'm not going to work out the math, because this ends up, if you notice, I've got derivatives with respect to z right there and right there. Now I have derivatives with respect to r, right? This is a PDE. And we're going to have to learn how to solve PDEs like this later. But I wanted to highlight the point for these force convection problems. That sort of when you set them up and look at them, right? We've been talking, like the hard part about the mass transfer has to do with how the velocity couples in, right? So in the problems that we did from the first two examples, or the second example last time where we did the convection velocity, we didn't need to use the equation of motion, the Navier-Stokes equation. All we needed was the total continuity. So that's what allowed us to solve for the velocity. In the forced convection case, okay, where what's driving the flow here is pressure, right? Now we can use the equation of motion to solve for the velocity. Okay, so to sort of summarize the different cases then, so if we're solving these diffusion problems, the easiest ones are the no convection cases, right? So I'm in a solid or it's very dilute. That was our first example. That's easy to do, right? You just solve the no convection case. You throw away the velocity. That's easy. Okay. The second one that I think are harder, okay, are the induced the diffusion induces a convection, right? In that case, that's where we have to do this solve for the total flux thing. Okay. And like I said last time, you can set up an equation like this, okay, and then you can write the total continuity equation instead of the equation of motion. And what that amounts to the same physical thing. You have to kind of do the same manipulations. You'll have to rewrite it in terms of the total flux and the solve for that. And that's how you'll plug that back in here to get that out. Okay. The third case is these forced convection problems. And the forced convection problems, these are decoupled, okay? So you can solve this first. I mean, they're not completely decoupled. You can solve this first and then this one. So they're sequential. So you solve a fluid mechanics problem, and then you do the mass transfer problem, okay? And then the last case is the one we're going to spend the rest of today on, and then some of the next time on at least, which is free convection, okay? And that's the kind of the opposite case. That's where I have fusion, I have a concentration gradient. The concentration gradient gives rise to a density gradient. That drives fluid flow, okay? So is equal to minus grad P plus mu grad squared V plus, and then we have this mu over 3 plus kappa del, well, that was the worst del of all time, del squared V plus rho G. Okay, let's see, that. Okay, so this one is the momentum equation, but I assumed that this one is Newtonian, but still compressible. Okay, so maybe the thing to say about these equations of change is I've assumed Fick's law, Newton's law of viscosity, and we'll do Fourier's law. Okay, so we're going to assume those force flux relationships that we've spent so long talking about. Okay, but I've tried to keep everything else as much as possible without assuming it, right? Okay, so that's momentum. So for energy, Okay, so for energy, we need to do a little bit of work. So there's a couple, so we need to do some work. It always seems like the energy equation's got the roughest time, right? Like we spend like a whole day just trying to get the energy equation from the balance to like the internal energy equation. So it's kind of a, so for a single component, remember we had the molecular flux was minus K grad T. That was just Fourier's law. But now we need to take into account any enthalpy that's being diffused across as well. Okay, so for multi-component, we now have Q is equal to minus K grad T plus, and then we have a sum over alpha from 1 to, this is NS, just bad handwriting, H alpha bar, M alpha, J alpha. Okay, so let's define these terms a little bit. So this is this guy is the partial molar entropy, or enthalpy, excuse me, partial molar enthalpy. Okay, thermo nightmare going off in your brain. Okay, this is our diffusive flux. And this is the molar mass. Okay, so that guy's going to have to get added in. That's kind of a bummer. All right, and then let's see. The other thing is we need to take into account. So that's, you know, the, what do I call the molecular flux addition. The other thing we need to add on is for chemical reactions. Okay, so it's like all your worst nightmares. Like if you imagine this problem, right? Like it's all of your classes at once, all in one problem. Okay, that's like what we're trying to get to, which is why it's not very useful. So now we have to add this other term that has the partial molar enthalpies and the reactions. Okay, so now this is the reaction rate. Okay, so we're going to have to add that term on. And that should take care of our heat of reaction that's changing energy, right? So in the end, what we can write, so those terms all come together to give us this. So rho C sub P hat, big D T, D little t, is equal to minus grad Q minus tau double dot grad V plus, and it gets rewritten a little bit here for a mixture 2, d log V, d log T, at constant P and XA, dP dt. And then I have to go on a second line, maybe you will too, plus the sum over H alpha, the divergence of J alpha minus R alpha. Okay. And this Q here, that Q is what we said right over there. Q is minus K grad T plus the sum from alphas 1 and S. So then I rewrite it as this, make a point. Okay, and I'll talk about this one too, just to remind us. This one is the mu phi V plus kappa psi V. Well, that's the 20. Okay, I get all that. Okay, so the thing to point out here is that this J right here, this J alpha, this is C alpha V alpha minus V. So this is the molar flux relative to the mass averaged velocity. Okay, so in the past we've been using either little j or big J star, and it happens to be in this one, it's easier to write with this guy. Okay, so this is the giant nasty mess. Okay, so there is a whole, let's see, to solve stuff, we also need equation of state, which is rho t and for all of the x alphas. So that would be like an equation of state with mixing rules, okay? And we would need some equation for the internal energy, which is how we're going to get heat capacities. Okay, so just takes that long to write them down. I hope you never have to do a problem with all this. Okay, so this is obviously very general. So that's maybe what I'll say at the end here. Very general. Okay, so sometimes it's nice to see that all out, to see kind of how they all fit together, to see those cases. Okay, this could be any of that. We talked about all these simplifications. So it could be solids, liquids, gases, right? It could be compressible, it could be incompressible, reactions, no reactions, dilute, not dilute, right? We haven't assumed hardly anything. The only thing we've assumed here is that it's Newtonian, that we have fixed law and Fourier's law, right? And some people even mess with that sometimes, right? So if you wanted to mess with those, these would go back to being the J alphas here, right? And you could put, instead of this piece here, you could have like a del dot tau, right? And you had the Q already over there, that one will stay the same. So if you wanted to make it non-Newtonian, you could mess with the tau, right? And if you wanted to mess with the flux expression, mess with that guy, okay? So, yes.
Sorry, what is the Newtonian parentheses thing pointing to? Is that pointing to the tau?
This is this term, right? So remember that was the tau double dot grad V. That was where we get grad V dot grad, double dot grad V, that give this term. And then there was the terms that had the divergence of the velocity that came in this term. So, okay. So I hope like you probably got taught like I did as a undergraduate to start with like the general equation and simplify from there, like that's a useful way. And I hope you never do that for this, okay? Like it's too much, right, to start from here. So you kind of like in transport, you kind of have to start assuming something, right? Or you can't even write stuff down. So that you start to get to this point where there's so many kind of assumptions floating around in your head. You just have to be careful and be clear on what it is you're assuming. And so I think that's one of the really important pieces that I hope you're getting out of this part of this class, is that like, it's not that it's like all theories involve some kind of assumption. And this is theory. Like don't mistake this. Like this is, how we understand transport. But we have to make some kind of assumptions. We have to start somewhere. And a lot of times it's actually more useful to start in a case that you can solve where you've made a lot of assumptions and then generalize, as opposed to starting at the like everything and then simplifying your way down, right? You just have to be careful that you're not assuming something stupid. And some of that, what does it mean to assume something stupid? Well, sometimes you don't know, you do, and then you realize later. But you start out and you reason about it, use your past experience, okay? And then in real life, when you're doing these experiments, right, you might try the easiest thing first and see if it fits your experiment. Like you can see, like Kussler had this really nice line in his book I was reading as I was looking at that. He says, a lot of people who are theorists like me get all excited about the math and just start going, okay? And you're like, oh, I have to assume this, and I feel, oh, I can do this. And you just sort of make it complicated until you can do as hard a math as possible. But most of us, and even the theoreticians, right, should realize that like what you should do is get the easiest thing possible, okay? So, plug flow, right? Don't solve with the velocity distribution first, right? Do the easiest thing you can do. See if that matches what you're trying to explain. If it doesn't, then start to think about what are the different terms in here that might affect my answer and how I'm seeing this in the experiment. What assumptions should I relax, right? And so in a way, this tells us like, this would be the worst case scenario, right? That you had to relax all the way back to here. And if you do that, you've done something horribly, horribly wrong, right? Like if you have to retreat all the way back to here for all the equations, something went wrong somewhere, okay? You're putting this in a computer and you're basically not doing any theory anyway, because you're just calculating the thing with all the nasty mess in it. You probably have 1,000 parameters and it's gonna not be that insightful, right? So, all right, I've rambled enough about that. Let's start on the Boussinesq approximation and we'll see where we can get in 5 minutes. Questions while I'm erasing?
So I've used the Boussinesq approximation in CFD, where you assume essentially that density is not applicable except for when it's multiplied by a gravity term, or something like that. Is that,
That's what we're getting to. Yep.
that's awesome.
Maybe I just wanted you to appreciate the Boussinesq approximation for a moment. I don't know. I wanted to see that all out for myself. I hope that wasn't a complete waste. Okay. So B Boussinesq approximation. Okay. So, so we just assume things like Fourier's law, Fick's law, whatever. It's often, it's a great simplifying assumption to assume incompressibility, right? Like if you assume something's compressible, that makes your life really hard. You have equations of state going on, you've got all sorts of nastiness, okay? But we often have these cases like where air rises because it's hot, where clearly there's a density difference, okay? And so it's a real pain if you have to retreat all the way back to the compressible equations, right? Remember, we were writing that up with dP. That's just this nasty mess, okay? And it makes the fluid mechanics a lot harder too. So we like something that's like incompressibility, but where we can still have density differences, okay? Now that seems like cheating, okay? And it kind of is, but let's try, okay? So what we're gonna do, so I'll put that up here. We would like incompressibility. I'll put that in quotes. Even when rho is not constant. Okay? So what we're going to do is we're going to write a new equation of state that's our like simplified equation of state. Okay? We're going to call this we're going to do a Taylor expansion about the density. Okay? You guys have done Taylor expansions, I assume. So we're going to do rho is rho average plus d rho dt evaluated at t bar and the average WA. Sorry for that rho. Let's see. And this will be t minus t bar plus d rho dWA evaluated at rho bar WA bar. Why did I put rho? Shouldn't that be t? That should be t. T WA multiplied by rho minus rho bar plus higher order terms. Oh, not rho. Oh, goodness. Okay, so this is just a Taylor expansion. I'm saying the density is like some average density, something that I'm going to pick, okay? And then I'm going to say there's a density difference due to temperatures and due to concentrations, okay? And now this often gets rewritten because this term in particular has a thing that we often write in thermo differently. So we often write in thermo this parameter beta, which is minus 1 over rho d rho dt at constant P, okay? That's the isobaric thermal expansivity, mouthful, but thermal expansion coefficient, right? How much does something change? So instead of writing this, like with this d rho dt, people will write it with beta, okay, instead. And then we're going to define another one over here as zeta, which is equal to minus 1 over rho d rho dWA Well, I don't know what it's constant at. I'm kind of a little confused on that as I'm writing this. So I'm gonna, so then what we're gonna do, right, is this is just gonna be a rho multiplied by the zeta and a rho multiplied by the beta, and I'll be able to put those guys up there, right? So I'm gonna evaluate them at rho bar, okay? So I'm gonna get rho is rho bar plus, or excuse me, minus, because I have a minus sign, minus rho bar beta bar T minus T bar minus rho bar zeta bar WA minus WA bar. Okay. All right. And you might think we're about done. We'll stop here for the day. Okay. But you might think, well, this is kind of dumb. Like, can you really just do this? Right. But it turns out that for most liquids, for example, beta is usually about a constant. Okay. So this isn't that dumb of an approximation to use, okay? It's a pretty good approximation when you have, say, temperature change. It's going to give us something, all right? And what we're going to do is take this rho bar and we're going to treat the fluids like Andrew said, that everywhere is a constant density, except in the gravitation term, where we're going to throw this other piece in, okay? And that's going to give us an extra forcing term, an extra force that's going to, give like rise or fall to our fluid, and then everything else is going to be easy, right? Because it'll look like incompressible, all right? So that's what we'll talk about next time. We'll do that. We'll do some free convection problems and okay.